Thermodynamics. Thermodynamics. In thermodynamics, we study the relation between heat energy and other forms of energy like chemical energy, magnetic energy, light energy, etc. In thermodynamics, we study the relationship between heat energy and other forms of energy. Here, we study the internal state of a system. We use the following parameters. We confine our study to gases and we study gases with the parameters pressure, volume, temperature, entropy, internal energy, etc. Pressure, volume, temperature, internal energy, entropy, etc. Zeroth law of thermodynamics. Zeroth law of thermodynamics. This law defines temperature. This law defines temperature. Heat flows only when there is difference in temperature. Heat flows only when there is difference in temperature. If no exchange of heat takes place between two bodies or two systems, if no exchange of heat takes place between two systems, then they are said to be in thermal equilibrium. Their internal activity will be the same. The internal activity of such systems will be the same. We can define zeroth law like this. If two bodies A and B are in thermal equilibrium with a third body C, if two bodies A and B are in thermal equilibrium with a third body C, then A and B will also be in thermal equilibrium. A and B will also be in thermal equilibrium. Heat and its units. Heat and its units. Heat is a form of energy. Heat is a form of energy. It flows from a body at high temperature to a body at low temperature. It flows from a body at high temperature to a body at low temperature. Its unit is calorie in CGS system and joule in SI system. Its unit is calorie in CGS system and joule in SI system. Definition of calorie. It is the amount of heat required. Calorie is the amount of heat required to raise the temperature of 1 gram of water through 1 gram of water through 1 degree centigrade. 15 degrees calorie. 15 degrees calorie. 1 gram of water at different temperatures requires different amounts of heat. That means the amount of heat required to raise the temperature from 1 degree centigrade to 2 degree centigrade is not the same as the amount of heat required to raise the temperature from 98 degrees to 99 degrees. So, the amount of heat required changes with the temperature. But if we take the average of the calories from 0 to 1, 1 to 2, 2 to 3, etc., then it is equivalent to 15 degrees calorie. It is equivalent to 15 degrees calorie. So, we define 15 degrees calorie. It is the amount of heat required. 15 degrees calorie is the amount of heat required to raise the temperature of 1 gram of water from 14.5 degrees centigrade to 15.5 degrees centigrade. From 14.5 degrees centigrade to 15.5 degrees centigrade under atmospheric pressure. Mechanical equivalent of heat. Mechanical equivalent of heat. Whenever work is done, say heat is produced. Whenever work is done, if heat is produced, then the amount of heat produced and the amount of work done, the amount of heat produced by the amount of work done is a constant. For example, if W units of work is done and thereby Q units of heat is produced, by doing W units of work, if Q units of heat is produced, then W by Q is a constant. W by Q is a constant. This constant is indicated by J. This constant is indicated by J and is known as mechanical equivalent of heat. Mechanical equivalent of heat. Generally, W is measured in joules. Generally, W is measured in joules and Q in calories. Q is measured in calories. So, J is measured in joules per calories. J is measured in joules per calories. The value of J is 4.186 joules per calorie. The value of J is 4.186 joules per calorie. That is, to produce 1 calorie of heat, 4.186 joules of work is needed. 4.186 joules of heat is needed. In SI system, both work and heat are measured in joules. In SI system, both work and heat are measured in joules. So, the value of J becomes 1. So, it disappears in SI system. Internal energy. Internal energy indicated by U. Indicated by U. Internal energy arises due to potential and kinetic energies of the molecules and atoms of gas. Internal energy of a gaseous system, it is due to the potential energy and kinetic energy of the gas molecules and atoms. Potential energy arises due to interaction of one atom with another, one molecule with another molecule, or one atom with another atom in a molecule. It arises due to electrostatic attraction of the molecules and atoms. Electrostatic attraction of atoms and molecules. Hence, interaction of the molecules with one another gives rise to interaction of molecules with one another gives rise to potential energy. And kinetic energy is due to the translatory motion, vibratory motion and rotational motion of the molecules. Kinetic energy is due to translatory motion, rotational motion and vibrational motion of the molecules in a gas. So, the internal energy is constituted by the potential and kinetic energies of the molecules of the gas. The temperature of a system is a measure of its translational kinetic energy. The temperature of a system is a measure of the translatory kinetic energy of the system. Translatory kinetic energy is 0 at 0 degrees Kelvin, but the molecules will have potential energy due to vibrational motion of the atoms. Vibrational motion of the atoms. This is called 0 point energy. This is called 0 point energy. If a gas is compressed, its internal energy increases. If the increase in internal energy is due to the kinetic energy of the gas molecules, then the temperature increases. So, the internal energy, potential energy increases. But if the energy is used by the electrostatic potential energy or vibrational or rotational kinetic energy of the gas, then there will be no increase in temperature. The temperature depends on translatory kinetic energy of the gas molecules. So, in an ideal gas, that is the gas which has only translatory kinetic energy, the temperature change depends on the change in internal energy. The temperature change depends on internal energy. The first law of thermodynamics. The first law of thermodynamics. This is nothing but the conservation law of energy. This is nothing but the conservation law of energy between heat energy and work energy. Heat energy and work energy. Mathematically, we have the relation W by Q is equal to J. W by Q is equal to J. That is the relation between mechanical work and heat energy. Therefore, for a particular quantity of mechanical work, a definite amount of heat is produced. For a particular quantity of mechanical work, definite amount of heat is produced. So, by utilizing a definite amount of heat energy, we can obtain a particular quantity of mechanical work. By utilizing a definite amount of heat, we can obtain a definite quantity of mechanical energy. Like this, there is a relation between work done and heat energy. This relation is called the first law of thermodynamics. The first law of thermodynamics is stated mathematically as delta Q is equal to delta U plus delta W. Delta Q is equal to delta U plus delta W. Here three quantities are involved. One is heat energy, change in internal energy and work done. Three forms of energy are involved here: heat energy, change in internal energy and work done. Delta Q is heat energy supplied or given out by the system. Delta U is change in internal energy, that is either increase or decrease in internal energy. Delta W is work done either by the system or on the system. So here three types of energy changes takes place. The relation between the three types of energies is given here. From the above relation, what we understand is, if delta Q amount of heat energy is given to a system, if the amount of heat energy given to a system is delta Q, then the part delta U is utilized in increasing the internal energy, and the part delta W is the external work done by the system. So the amount of heat given to a system is utilized in two ways. In increasing the internal energy, a part of it is used. In increasing the internal energy, another part appears as work done by the system. In general, we use this relation. For using this relation, we take the following sign convention. Heat given to the system is taken as positive. If the internal energy increases, then it is considered as positive. The increase in internal energy is considered as positive, and work done by the system is taken as positive. Heat capacity. The amount of heat required to raise the temperature of a body through 1 degree centigrade is called its heat capacity. The amount of heat required to raise the temperature of a body through 1 degree centigrade is its heat capacity. Its unit is joule per Kelvin. By giving delta Q heat, if the rise in temperature is dt, by an amount of energy dq, then heat capacity is dq by dt. Specific heat capacity. It is the amount of heat required to raise the temperature of unit mass of a substance through 1 degree centigrade. It is the amount of heat required to raise the temperature of unit mass of a substance through 1 degree. In SI system, the unit is joules per kg per Kelvin. The temperature is measured in Kelvin. In SI system, the unit is joules per kg per Kelvin. If dq is the heat given to a body, of mass m, and thereby the rise in temperature is dt, then specific heat capacity is equal to 1 by m into dq by dt.